In this video, I want to continue an example that we started in class where we were making this data type called state, and the idea is that a value of type state SA represents some kind of computation that will eventually produce a value of type A, but along the way it has access to basically a mutable variable of type S. And we represent this as a function that takes the original state of type S and will return a new state of type S and a value of type A. And the point is that we'll be able to chain these together so that the next one, as its original state, will take the output state of this one. And so as we chain them together, we'll see changes to the state propagating through. So we had written some of this code in class, but I'm just going to go over it quickly again in this video. So we can make an instance of functor for state S. So how does this work? So fmap will need to take a function from A to B and a state SA computation and return a state SB computation. Let's see. Need to enable instance sigs. Okay. So we take a function G and a value of type state SA, which we can pattern match on it and say it's S, and then we'll call this function K. So remember that, right? So now we have G, which has type A to B. We also have K. So since this SK was a state SA, yes, that's right, a state SA. It's this here. Then K, what's held inside of it is a function of this type. So K is going to be an S to a pair of SA function. So we need to make a state, so we'll use the constructor S, and we need to make a function from S to SB. So I will take my S. Now if I run K on S, right, that will give me a pair of an S and an A. What I really want is a pair of an S and a B. And I think in class we just pattern matched on it, and we mentioned that you could use this function called second. But actually I realized we already wrote an instance of functor for a pair type, and in fact when you do fmap, it changes the second part and leaves the first part alone, which is exactly what we want to do. So another way to do this would be to say fmap G ks. So ks makes a pair of an S and an A, and then I'm going to fmap G, which is going to change the A into a B, and that's exactly what we need. So we can also make an instance of applicative for state S. So we need a pure, right, which is going to be from A to state SA, and this is easy. Pure A, we make a state, make a state computation. We take the original state, little s, and we return that same state unchanged and the value A. And then for the app operator, so we can say, so we need something app something. So let's write down the type of it actually. So it's going to take a state computation that produces a function from A to B, another state computation that produces an A, and then we're going to put them together into a big state computation that produces a B, right? And what this output state computation is going to do, it's going to first run this, producing a function from A to B, and then it's going to take whatever the output state was from this computation and feed it as the input state to this computation, and then run this one, and then finally produce an A, and then we'll just apply that function to the A and get the B at the end. And the state updates that are going to happen will be sort of the composition of all the updates that happen from this one and then from this one. So we can pattern match on these and say S, G, S, call it X. So we want to make a state computation that takes a lambda S, and then I'm going to put this down here actually. We're going to need a lot of lines. What's the first thing I'm going to do with this state little s? I want to feed it into G, right? G is expecting an initial state, so I'm going to say G is going to then produce a pair of a new state and this function from A to B. So I'll say case GS of, that's going to give me an updated state, which I'll call S prime, and a function which I will call F. And then what do I want to do with that? Well, I want to take this updated state and feed that into this second state computation, which is, and that's represented by this function x. So I'll say, again, case x S prime of, and that's going to return another updated state and a value of type A. And finally, what we want to return is a pair of a state and a B. The state that we want to return is this final updated state that we got. And then we're going to get the B by applying our function f to the value A. I think I need a closing parentheses here. Yep. So that type checks. So to do some examples, let's go back and make a couple little kind of utility methods for dealing with states. So one thing we could do is we could make a put function that takes a state S. So the idea is that put will take a state little s, a state value, and it'll make a state computation that overwrites the old state with this new value for the state, and then returns unit. So this, I don't know if we've actually seen this before. So basically, imagine it like this. Unit is the type. It's a type that has only one constructor, which is also called unit, which is of type unit. So this is the completely uninteresting type because there's only one value possible of this type. So if you have a value of this type, it tells you nothing because there's only one thing it could possibly be. So we often use this to represent some kind of returned value that we don't care about, or something like that. This would be, so I mean, think of it like writing void in Java or C++ or something. We're saying basically this doesn't return anything interesting. So how does this work? Well, we take the little s and we're going to return a state computation that, so we make a lambda, but we're going to ignore the original state because we're just going to overwrite it. We're going to return whatever this value of s was, and then unit. Okay. We'll make a get, which is a state computation that returns the current value of the state. And so we can do this by saying, well, it's a state computation lambda s, and it returns, so it doesn't change the state, so the new, the state it returns is the same as the original state, but also the value it returns is also that state. Let's see, well, finally we can make one, let's make a modify function that takes a function from s to s, and it's going to apply that function to the current state in order to update it. So this is again going to be a state s. It's not going to return anything interesting, it just does something to the state. So modify f, we give it a state computation that takes the old state, and the new updated state is going to be f applied to that s, and then the output value is unit. Okay. So let's just try this out really quick. So, okay. If I say, actually, you know what, let's make one more, which is just going to be, call it run state, that takes a state SA computation and a starting state and returns the ending state and the value of type A. And really all this does is it just pattern matches on, like a function of this type is exactly what a state computation contains. So we'll just say that's what run state does. It just kind of unpacks that. So I can say, let's make, put 3, and then modify times 2. So the type of this is a state s unit for any numeric type s. And if I say run state of that, and I give it a starting state of 0, what I expect is that it's going to, first it's going to reset the state to 3, and then it's going to take the current state, which should be 3, and multiply it by 2. So I should get 6 at the end. And that's indeed what I see, right? I get the ending state was 6, and we got a unit out of it. Okay. So let's just do a couple more examples of how we might use this. So here's one function we might want to write. So this function says if you give it a list of ints, we're going to make a state computation that it doesn't return anything interesting, but what it does is it's going to accumulate all these ints into the state. So it's going to add every int in this list into the current state value. So how does this work? We could write this by pattern matching on the list and just kind of going through it recursively, but we can actually do something nicer. So down here I've written the types of a couple helper methods that work over any applicative that we looked at in class the other day. And in particular, look at this traverse. So this traverse says if you have a list of A's and some function that says for each A what kind of computation we want to run in some context of some applicative f, then we can do that for every thing in that list and basically kind of collect up all the effects into this single f. And in particular, that's what we want to do, right? We want to say for each int, I want to make a state computation that's going to add that int to the current state. So I want to say something like traverse. The function I want is the function that takes an x and then does something to the state. It does modify plus x. So plus x is the function that adds x to the current state. We're going to apply that to the state. Modify then is going to return a unit. So in this case, in the type of traverse, our b is actually unit in this case. I'm going to apply that to x's. And this is almost right. It's not quite what I want though, because notice this is going to return a list of b. So we're actually going to get a list of unit, but I really just want a unit. A list of unit is not very interesting. Right, so it says it couldn't match type list of unit with unit, but this is easy to fix, right? I can use this and then operator that says take this first computation and do all its effects, but ignore its output value, because that's what I don't care about the output value of a list of units. I just want to say, and then let's run the computation that kind of has no effects but just returns a single unit, and that's going to kind of fix up the return type that I want. So let's try this out. Vacuum sum 1 to 4. So if I run state of this, and with the initial state 0, right, I get 10, which is the sum of 1 through 4. Now, so far we've written a very convoluted, weird way of just adding up the numbers in a list. However, the point is that we can do more interesting things with this. So for example, let's make a different function that similarly it adds up all the ints in this list into the state, but also it's going to return a list of the partial sums along the way. So basically at each point it's going to replace each int in the list with whatever the current state was at that point while we were going through the list. How do I do this? Well, again, I don't have to do it explicitly recursively. I can just say traverse, we're going to modify plus x. The difference is that now in this, so before modify plus x just returned a unit, but I actually want to now return the current value of the state instead of returning unit. So I'm going to say, do this to the state and then ignore its output value, and the output value we want to return is just the result of doing get. So this will say get whatever the current state is and return that. And if I do that to x's, that's now going to do exactly what I want. So if we try this out, if I scan sum, or I say run state, scan sum 1 to 4, with a starting state of 0. I get the sum of 10 still, but now I get this list that's the partial sum. So it was 1, and then at this point, once we added the 2, the current state at that point was 3, and so on, right? I could do something like, I could start this at a different starting state. I'm going to get a different, state at the end, and different partial things. I can even do things like, so I can say, for example, let's scan some, 2, 6, 9. So I've now done scan sum on 2 different lists, and I'm combining their results with the pairing operator, right? All in this applicative state context. But the state is going to carry through both the computations. So what we're going to see is a sort of running total as we go through. So this is the sum of everything in both lists, and we see like what the state was at each point along there as we went through. And you could do this, with a tree, and you could scan over a whole tree and add up everything in the tree and replace each thing by the cumulative sum at that point, or something like that. It wouldn't be that hard to write, a little adapter for trees that ran over it with basically a version of traverse for trees instead of for lists. And there's other things you could do with this as well. So that's a nice little example, and you'll see something similar to this, and even cooler, and even more practical on the homework, where you'll be doing stuff with parsers, which actually has a lot in common with this state thing, but it's got a little bit of extra bells and whistles on top of it.